Hey guys, welcome back. Day 19, continuation from day 18, and we'll just continue with the problems. Suppose a hydrocarbon, that's just carbon and hydrogen, is burned and produces CO2 and water. Well, what does that mean? Hydrocarbon would be C and H. C, we don't know. H, we don't know. Burned. Burned means what? We add O2. And it's going to produce CO2 and H2O. In fact, this is a picture of the compound. We don't necessarily know that yet, so maybe you could Google the image, I don't know, but we'll get there. We'll get to what it is. All we know, so we can't balance an equation. We haven't even talked about that yet. We can't balance this because we don't know what CH, the hydrocarbon, is. We know that the number of moles of CO2 produced is 1.5 times the number of moles of water produced. So that means if there's 1 mole of water, there's 1.5 carbon dioxide. What's the empirical formula? Well, if all of the carbon comes from here and all of the hydrogen is there, I can come up with something, can't we? I can see that there is C1.5 H2, right? Because there's 1.5 C's and 2 H's. But we can't have that, can we? We can't have half a carbon. So that would mean it would be C3H4 would be my empirical formula. So we got basically a reaction, kind of, because we can't balance it. We got the mole ratio of C and the H from both sides of the arrow. We got the empirical formula because we made whole numbers. Now we got to do the molecular mass. So we know the molar mass is 120. So the molecular, which is this thing right here, is 120 grams per mole. The empirical, 12 times 3, which is 36, and 4, 40 grams per mole. So 120 divided by 40 would be 3. So I need 3 empiricals. So I times that by 3 to get C9H12. And there's my molecular formula. That's what that is. And so the carbons are obviously 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are the carbons. The hydrogens, 3, 6, 9. We'll learn there's 1 here, 10, 1 there, 11, and 1 there, 12. Now, you don't really learn that into organic chemistry, but that's what it is. So that's C9H12. Number 8. Number 8 is combustion analysis. So where we burn a sample to figure out what we have. We get the percent of carbon, percent hydrogen, percent oxygen. Sometimes there's even CHN where they do percent nitrogen. And we like this because it helps identify what we made. Again, if you have all these white compounds, you don't know what they are. How do you know what they are? Tasting them is not always a good idea. Like in the lab, it's never a good idea. So combustion analysis happens to be one of my top 5 favorite types of problems. We'll get 5 problems this year that are my top 5 favorite types of problems. That does not mean this problem is the exact one you'll get. Problems like this are the ones you will get. Okay? So don't just memorize this problem. You memorize this problem, not going to go so well for you. So number 8 here. 0.1101 grams of an organic compound containing C, H, and O. So we have C, H, and O. I don't know what those happen to be. C, H, and O. And that is burned. O2. Give me CO2 and H2O. Well, what do we know? We know I have 0.1101 grams of my unknown, excess oxygen, and we have 0.2503 grams of carbon dioxide and 0.1025 grams of water. So now all the carbon here goes to carbon dioxide. All the hydrogen here goes to water. Oxygen's in everything. So I need to figure out how much carbon is in my original sample, how much hydrogen's in the original sample, and how much oxygen's in the original sample. Well, I have grams of CO2. I can get grams of C out of that. So I'm going to take 0.2503 grams of CO2, and we're going to do some conversions. Carbon dioxide weighs 44.01 grams of CO2 is 1 mole CO2. We know that for every 1 mole of CO2, there is 1 mole of C. And 1 mole of C is 12.01 grams of C. So what did I just do with this conversion? I'm taking my grams of carbon dioxide, I'm converting it to moles. I have a mole ratio of carbon to carbon dioxide. There's 1 carbon for every carbon dioxide. So in my 0.2503 grams of carbon dioxide, I can figure out how many grams of carbon there are, and there happens to be 0.0683. I can do the same thing with my hydrogen. We have 0.1025 grams of H2O. We know 1 mole of H2, or 18.02 grams of water, is 1 mole of water. And we know that for every 1 mole of H2O, there are 2 moles of H. And 1 mole of H is 1.008 grams of H. So that gives me 0.01149 grams of H. So we figure out how many grams of C and how many grams of H were in our products. So now I want to take, let's not use that color, my mass here, take my 0.1101 grams of C, H, and O, subtract 0.0683 grams of C, and subtract 0.01149 grams of H, and I will be left with 0.03031 grams of O. And so now, if I look, I have 0.06830 grams of carbon, 0.01149 grams of hydrogen, and 0.03031 grams of oxygen. And at this point, this should look very familiar to us. Why? Well, I got grams. I just got to go to moles and find the mole ratio. So now we're going to divide by the molar mass of all 3 of these. So the molar mass of carbon, 12.01 grams per mole. Hydrogen, 1.008 grams per mole. and 16.00 grams per mole. For carbon, I get 0.005687 moles of C. For hydrogen, I believe I get 0.1138 moles. And oxygen, 0.01894. So that's what I believe I get. Now we're going to divide by the smallest one, which is oxygen, 0.001894. So for carbon, it looks like I get 3. Hydrogen, I think I get 6. And oxygen, of course, I get 1. So the empirical formula. C3H6O. The molecular. Happens to weigh, is it 115? Well, how much does my empirical weigh? 12 times 3, right? 36 plus 6, 42 plus 16, 58. This weighs about 58 grams per mole. So 115 divided 58 looks like it's 2. That means I have to multiply this times 2. So my molecular would be C, is red, C6H12O2. And there we go. So let's recap this. We figured out, all right, so many grams of carbon dioxide, so many grams of water. All the carbon came from carbon dioxide, or from carbon dioxide came from my unknown. All my hydrogen came from my unknown. So I took my grams of carbon dioxide and got my grams of carbon. Took my grams of water and got my grams of hydrogen. Subtracted the carbon and hydrogen from the original amount with carbon, hydrogen, oxygen. Only oxygen is left. So now I have grams of oxygen, grams of carbon, grams of hydrogen. Converted them to moles. Moles of carbon, moles of hydrogen, moles of oxygen. Divided by the smallest, get a whole number ratio, 361. Found the molar mass of that empirical formula and figured that 2 of them need to make up the molecular, so I took my empirical, times it by 2 to get the molecular. That's it. Number 9. Total number of atoms in sample of cocaine hydrochloride. Mass of 23.5 milligrams. Alright, so milli, of course, is 10 to the minus third, right? So 2.3, I'm sorry, let's try 23.5 times 10 to the minus third grams of C17H22ClNO4. Well, grams to moles. Molar mass happens to be 339.85 grams of C17H22ClNO4, 1 mole. C17H22ClNO4. Now, how many atoms? 17 and 22 plus 1 plus 1 plus 4. So that's what? 17 and 22 would be 39, 40, 41, 45. So 1 mole of C17H22ClNO4 happens to be 45. Well, technically, let's not do it this way. Yeah, let's do 1 mole happens to be 6.022 times 10 to the 23rd molecules. And 1 molecule of C17H22ClNO4 is 45 atoms. That's a little better. All right, we do that math. I get 1.87 times 10 to the 21st atoms. And that concludes day 18 and 19.